Well, it's a real pleasure to be here, an honor to speak to all of you. For me, much of my career, the work I've done with LISP has been really kind of a lone experience. I really haven't worked directly with other people doing LISP programming, although we've built up a little community over the internet in recent years, and that's been nice. But to actually come out, be able to meet everybody and speak, it's really nice, especially after the great Richard Stallman. That's such a pleasure. And Christian Koenig, I hope I pronounced his name right. I so much respect him and that great book, one of my favorite books, Listed in Small Pieces, which I think is one of the great books of computer science.
Very translated.
Yeah, it's very well translated. So yeah, to meet people from so many foreign countries, Germany and England and France and Boston. Good. Well, this talk is not about writing multi-threaded applications. It's a little more, more geekier than that, kind of like implementation of threads and things like that. So, if you've been here since this morning, this is the 10th talk of the day that you've sat through, which to me is sort of an astounding number of talks, and you're not done. There's several more to go. So, unfortunately, I don't have like a bunch of silly pictures and things and little banter to keep you from falling asleep. I'm just going to dive right into it and try and get through 50 slides or so. So, but I do have a few illustrations that I think will help to conceptualize some of these rather abstract concepts as threads and dynamic bindings and things. So as we go through, hopefully they'll help you get a mental model of the kinds of things I'm trying to talk about. So I guess I have to start here. I'm talking about threads, otherwise known as lightweight processes in the Lisp world. And I just thought I would mention, why we're going to this trouble. Modern applications tend to use multiple threads within a process. For a number of years, I've found that to be the case in applications I've been involved with. If you want to write a server for just about anything, certainly on the Windows platform, you're dealing with multiple threads. And modern languages, Java, C#, whatever, they generally will have some support for multiple threads built in. C and C++ compilers as they typically do. Well, bottom line, the last item, Lisp is cool and threads are cool. So I don't have anything else to say about that. This is where I try to stir up a little controversy. This is what I claim is the right way to think about threads. And I didn't even ever think this would be controversial, but all threads run simultaneously. I mean, to me, that's the concept. You divide up your algorithm and you say, I'm going to have this run, this run, this run, at the same time. And it's, it's a matter of implementation if they actually do or not, but it shouldn't be, a matter of me to concern myself with. I should construct it in such a way that if they do, great. And if they don't, because I've only got one processor, well, then the operating system will work it out. Something it'll look like they're running simultaneously. Thinking of threads this way forces you to consider performance and object locking, synchronization, sharing, all these issues right up front. I admit it makes thread programming tricky, but that's the nature of the game. As an architect, I always advise people when they're building an application, if you can get away without using threads, don't. It's like it makes the application an awful lot more complicated. But the fact is, as I said, most modern applications, they seem to creep in here or there. This is, in my opinion, the wrong way to think about threads. Multiple execution contexts within a process which run one at a time. To me, I don't really think as a programmer I should be thinking about switching between threads. I should just be thinking of them as running together because, in fact, if I have multiple processors, they should be. That's the goal. I shouldn't be thinking about thread switching logic that can be intercepted, you know, and what am I going to do when this thread switches to that thread and all that stuff. I mean, yeah, well, I know there's lots of reasons to do that. You know, there's lots of kinds of projects that might be a useful thing, but in the general case of application building, I think it's you know, I think it's better to leave that stuff to the operating system. And so, I don't know, it just seems to be a little controversial, so I just mentioned that. And I consider, you know, standard Windows API, like without interrupts, I consider that kind of a bad habit. You know, it's so easy when you're writing multi-threaded applications to say, okay, don't do anything else while you're doing this. Well, if you've got other processors, you're telling them, oh, just wait, go stop what you're doing. In fact, implementing it, as you'll see later, implementing this in a system like mine is pretty problematic. Here's what a thread looks like. That's an actual picture. That thread, I think if you look close, it's checking into Microsoft to see if it's been activated yet. He's good. That's a Windows XP thread. They all are a little different on the different operating system versions. My background with threading tended to be from other languages, C, C++, and Java. The Lisp work I did was all single-threaded. I designed Corman Lisp to be pretty much. I wanted to be able to do anything I could do in any of these other languages. If I was coding in C++ and there was some operating system feature, I wanted to be able to take full advantage of it. And so decisions about how to implement threads were kind of based on that, rather than trying to support some APIs that people were used to on other this virtual systems. How I got started with all this stuff with threads was an email from Rainer Josvig, some of you probably know. And as I was developing the first versions of this Lisp compiler, I had some email contact with him and asked him for some opinions about what I was doing. And he just, one of his first items, as I remember, was operating system threads, you know, native threads on your operating system. You just have to have it in your system designed today. And until then, I hadn't even, been considering this. I've been building this system and struggling and sweating over this generation and garbage collector, struggling and sweating over the code generator, all this stuff. And I was like, no, please. But from the moment I heard that, I knew we had to do it. There had to be a way to do it, and it just was kind of an obsession. And ended up spending a lot of time just going in and redoing lots of parts of the system to make it work for operating system level threads. So much of the talk today is kind of going over these things that I found I had to think about or change or make decisions about. Well, as I said, threads are an OS function, just like the file system. A little comment about Lisp implemented threads. In the Franz terminology, they're non-OS threads. I just discovered, so I just call them Lisp implemented threads. They're the virtual threads when you allocate a scheduler within Lisp. And here's kind of a diagram of the difference. If you look at the Lisp implemented threads, you have an operating system. This big box represents the Lisp process, and then you have one operating system thread, and then within that you have a bunch of Lisp scheduled threads that are, running different execution contexts, but they're basically all considered one thread by the operating system. So that's okay, but the operating system, is only going to run that on one processor at a time. So if you've got multiple processors, yes, even Windows systems can have multiple processors. If you've got more than one, then you won't be taking advantage of it. So OS threads basically means each Lisp thread is really the operating system has created it and given it to you, and can potentially run it on a separate processor if processor is available, or if you decide to. Well, we just decided to go to implement OS threads purely, just foregoing the list of implemented threads, and to go with whatever the operating system provided, being in Win32. And they don't really give you any control over scheduling. They really, the operating system schedules it, yeah, you can bump a thread up to, up to a high priority, but then that basically means that thread will run all the time until it's done. And then you're always calling the operating system. So you don't really, basically you can't really get into scheduling. And I actually consider that a feature. I think it's better in general not to try to get involved there. Now this is, when I started doing threads, I said, well, first I turned to the standard. The standard says nothing that I could find. And I'm sure that's intentional. And, but I just tried to figure out how some things worked. I was trying to imagine how things worked with threads. I hadn't really worked with a threaded list before. And my first implementation, I think I did something really stupid, like I did, the way I was doing dynamic bindings was, when I found a special variable, other threads could see it and see the binding. And obviously that's really the wrong way to do it. I discovered right off. But I thought I was doing what was required by the standard. So there was just a little bit of confusion based on language in the standard. But let's see. I'll discuss that in a moment. It's just a general list of the items that I think were affected by threads, the specific items. There's more things, but these are the things I'm going to talk about. Okay, I included some language from the J13 standard. And I just included this because this is all, this is really all I could find about the bindings of special variables. And I highlighted the words, all references to the dynamic variable in a program refer for the duration of the evaluation. So in my first way of thinking, I thought, oh, well, that includes other threads. But, well, then, as I thought about it more, you can't possibly want that. I mean, if one thread finds a dynamic variable and its execution context is seeing that, then another thread's probably using that variable for something else at that time, and it gets you into trouble. So this is some language I think needs some clarification in the case of multiple threads. And again, they talk about the duration bound by, it's all about duration and intervals of time, without any mention of execution contexts, which is appropriate, I guess, considering that threads weren't part of the standard. Well, that was a very tricky thing to implement. As I thought about it, I said, well, you've got to have per thread special variable bindings. And the way I had implemented special variables was basically there's a symbol and there's a symbol's value slot. Probably a lot of people have implemented it the same way. And when you bound to that, it sort of made a stack. It pushed a new value on there, and then when you exited that scope after that duration, it popped the stack. And there's one place. So if you have multiple threads, well, where are you going to put all the different bindings, to keep separate? And there's, of course, a lot of discussion. People have studied shallow binding and deep binding and different implementation techniques. And I wanted something that was optimally efficient, but that was still per thread. I didn't want to go down a list of bindings. I wanted to be able to set a special variable over and over in a tight loop and still get decent performance, et cetera, et cetera. So I came out with a method that seems to work pretty well and keeps them all separate. I'll have to go through it a little bit. Basically, the top level binding is a binding that, I'll call it the top level binding, I don't know a better term. Basically, a variable has a binding that's shared by all the threads. So, sometimes that's what you want with threads. You want all of them to share some specific variable or setting. But when you use let or let star or whatever to bind a variable, then you're going to, actually, that's going to be something that only that thread sees. And one thing that we figured out is that we need to put basically we need to keep a table for each thread. We need to keep a table of these bindings. And only values slots that actually had compiled with let or let star or something actually had to be in that table. We didn't have to put every single value that could ever be declared special, in there, just ones that were actually used. So if you look here, this is some top level bindings of X, Y, and Z special variables, little circles of the bindings, and then what we did is we put pointers to those into a master symbol table. So you can access it either directly from the symbol slot or from the symbol table slot. And then when you actually have a thread or multiple threads, you copy the symbol table, the master, into one of those thread symbol tables. And what this diagram is trying to show is that the X, Y, and Z in one thread are all pointing, the top thread, thread 0, are all pointing at the original top level bindings. Yet in the thread 1, a couple of the bindings for the Y and Z bindings have been, new ones have been created using let, let's say. And it turns out to be pretty efficient just to copy this master symbol table when a thread is created and keep track of the bindings that way. You have just as good an efficiency as you would if you were only running one thread. This took a lot of work. Just a lot of work in the implementation. And David seemed just head scratching and trying to figure out whether this was the right way to make things work or not. But actually, I think it came out real nice. And one thing I discovered that actually started to do thread programming was it gave you a really nice way to make essentially global variables that are shared for a given thread. A lot of languages, most languages that support threads have some way to do well, Java calls them thread local, and in C# they're called thread static. But it's essentially like a variable that every function can see, but that's specific to the thread. And every time you allocate a new thread, you allocate another binding for that. And just this little change to the language really makes thread local variables just free in Lisp. You can bind to your heart's content, and only that thread can see those. And that actually is very elegant. I think it actually makes the nicest implementation I've seen, the nicest environment to program threads in.
In the previous slide, you have the thread local symbol tables. I thought earlier you mentioned that you have not copied all of the symbols, or are you saying you actually did?
Yeah. Okay, you're right. This symbol table doesn't contain all the symbols. It only contains an entry for every symbol that's been compiled using let or let star, where there's actually been a binding done in some code that's been loaded.
Anywhere, not just the spread.
Anywhere. So when the compiler runs, when Corman Lisp is only compiled, there's no interpreter, so it always compiles on the fly. So when it loads some code, compiled or not, for each symbol that's bound to, it triggers a thing that updates, that adds an entry. And actually, if there's multiple threads running at the time, it adds an entry to every table at that time.
What about probe D?
Excuse me?
What about probe D, which finds special variables not visible in the file?
Probe?
Probe D.
Probe D.
Probe D, okay. I'm sorry, I was not hearing very well. I was called it frog B, but who knows? Who knew? So, yeah, I'm sorry, I can't tell you off the top of my head how that's implemented. I believe it adds entries to this table, and prog v, that's a special special operator, right? And it's a good thing it is. Obviously, it has to do some specific things, and in this case, one of the things it has to do is has to allocate these things. But I'm not 100% sure on that. By the way, the source code is all available if anybody wants to look at it, see how it's implemented. So just talking about the thread local variables, here's a little example from Java where I might write a little run method that's going to be run each instance of it in a separate thread. And I want to make sure that I have a separate instance of this hash table, called stuff, that are referred to that way. And so, I create a thread local object and I instantiate it. And you see at the beginning of the last statement, all those silly parentheses that I have to use to get things, cast things, stuff like that. And here's the list version that does the same thing. I think it's a lot more elegant. It has fewer parentheses and no braces. So on the subject of bindings, I have a little picture of it, a dynamic binding that it just helps me to conceptualize what they look like. The only thing that matters is the symbol and the value, those two items there. Garbage collection. What can I say? That's where the fun lies. As much trouble as I thought it was to implement a generational garbage collector, with threads, it just made it a new dimension of fun. And basically the problem is, and this is again coming back to Windows, I can get interrupted between any two instructions, and I mean any two instructions. I mean, I really, in that interruption, garbage collection happens. The whole world can get swept away, including all of the code. All of the list codes in that same heap that gets moved around. So, making that work is kind of fun. And lots of papers have been written on it, and we spent a lot of time, trying to, come up with strategies. It certainly impacts code generation and garbage collection along with threads and along with foreign functions. Those are the big three, together they just make this challenge of a common list system huge. But there's a couple of strategies to garbage collecting here in a multiple threaded system. And one is you could just stop what they like to call the mutator. I love that name, mutator. Stop the mutator. Go out and do everything you have to do, move stuff around, traverse your routes or whatever, and then restart the mutator. And in general, if you're working on a single processor, that's pretty good. You could get really good average performance. The cost of garbage collection can be quite reasonable because their algorithm is pretty simple, really. What you have to do during the scan and move phase and everything is pretty simple. There's other ways to do this where you use parallel execution and you try and take advantage of multiple processors if you have them, and that would be nice. Certainly if you have a lot of processors, you're going to end up probably with a lower overall cost of garbage collection if you could have a separate processor running or something. And you minimize garbage collection pauses. But I think overall you can get more. My feeling, research I've done, is you're likely to see on a single processor system possibly more overall time because you're running algorithms incrementally. While it might keep the pauses down, you might get overall greater time. And the algorithms are certainly more error prone just because they're running in multiple threads more. And I just, being as this is one of the most the tricky parts of the system, and it's tired of, it's hard enough debugging the single thread version. I just went for a collector that stops the other threads, does its job as fast as it can, and it's actually quite fast because it's got multiple generations. The level zero generation collector usually happens within 2 or 3 milliseconds. And certainly for human-oriented interfaces and things, it works fine. It doesn't meet the 100 microsecond, real-time criteria, we heard about earlier today, but works for an awful lot of things. And I don't have to hack the code generator too much. As much as there's no read barriers or write, a little bit of a write barrier actually that the ephemeral collector uses, but I do that with hardware and software. So the algorithm that collects these basically it suspends all of the executing threads. If any threads in an atomic block, I'll define that what that is in a minute. Then it resumes that thread for a few milliseconds to try to get it out of an atomic block. It performs its root analysis on all the stacks, heaps, and everything. Copies live data from generation 0 to generation 1, and then triggers other levels that it has to, and then resumes any executing threads when it's done. And other things happen here too, but that's the basics of it. Well, if I didn't have to deal with multiple threads, you kind of guaranteed that the garbage collector happens in a safe spot because it's almost always going to be like a heap allocation. And when a heap allocation happens, you're in let's say all the heap allocation happens in one function. You're basically always going to be sitting at that same spot in the executed code when the garbage collector gets triggered, and that makes the job somewhat easy of figuring out your stack, figuring out your registers, figuring out what the pointers are. But in a multi-threaded system, as I said, it can happen anywhere between any pair of instructions. And some things that we do leave data in a state that the garbage collector is not going to recognize. It's not going to recognize if something's a pointer or an integer, or it's going to halfway have built up a new valid object. It's not going to be complete. So in the code generator, we had to come up with a way to tell the collector stay away during this small set of instructions. And some optimizations you could do too if you have that. So we had to come up with a way to flag sections of instructions. Other implementations I know will go in and will say collection can only happen at a specific spot in the code. And they'll describe a safe spot as, they'll maybe set up a safe spot before a return branch or something. But we chose not to use that method. We wanted to have minimal impact on the code generation. Instead used a pair of instructions and a processor flag. Oh, there's me after debugging the garbage collector one night. I don't know how that got in there. But that actually is pretty much what I went with. My figure is kind of filed down to points from coding all night. The foreign calls are basically calling out to other functions or getting called back by other functions, such as Java or C or C++ or whatever operating system calls. That poses yet another issue, because I don't know, I could be in a foreign thread or I could be not in a foreign, and it's like the garbage collector's got to go through these threads, these stacks, and it's got to sort all this stuff out. And we want to do minimal record keeping while we're executing because we don't want the code generation to be impacted too much. We're trying to keep maximum performance, optimum performance. So, as I say, it could be an unpredictable state. Foreign functions, we pretty much just have to. One way of thinking about foreign functions is that if you're in a foreign function, you're not executing Lisp code. So you can assume you got there by one of these thunks that happens between Lisp code and foreign code. And in that process, it's not going to leave any piece of data, halfway set. So if you're in a foreign function, it's actually usually a safe state. You don't need to worry about it. Mainly, we just have to know if a thread is executing foreign code, then we know for sure it's not executing Lisp code. We don't have any API for passing Lisp data directly to foreign code. So we can consider that a safe state. And then we get back to the other thing we have to do is we have to say, if you're in Lisp code, when is it safe to get called? So the code generator is cooperating with the threading by register, using standard register conventions and standard tagging conventions. The function call stack is really important. On the Windows, in an Intel system, you've got EBP and ESP that are actually threading the call stack frame, each time you do a call and return. In Corman, those can't be optimized away. The garbage collector has to have those, at least in Lisp code. In foreign code, well, they may have been optimized away, but nothing I can do about that. So we just have to have a way of detecting that it's foreign. These are all areas that a code generator the code generation kind of has to be concerned with. Stack frame links, the function calling and returning, foreign code transition, that's something I talked about. Some optimizations are just impractical. I found, to my thinking, they're impractical because you're trying to optimize something in a way that you're caching some piece of a Lisp heap object that's not really a valid piece. So we have to be pretty tight in the code generator about only doing a modification of an object that would leave it in an unsafe state within a really small segment that we call an atomic block. And I just created a pair of instructions. They're actually just renaming of real machine instructions. Begin atomic and end atomic. I just borrowed a processor flag, the direction flag, which the Lisp code generator never uses that to do anything. And we don't use those instructions because they're not really optimal on modern processors anyway. So it uses the direction flag to tell the garbage collector, if it kicks in, that some piece of code's an atomic block and to let it finish. So if the executing thread is between these instructions, then that flag is going to be set, and the garbage collector will give it a little more time to get out of there. One other thing I had to come up with, a virtual safe place is sort of like an atomic block, but it doesn't actually have those instructions around it, and that's just entering and exiting functions. Because as you're entering and exiting functions, it takes a couple of instructions to tear down the stack frame, and the garbage collector catches it in the middle. It's really messed up. So it actually just looks at the processor, it looks at the instruction pointer. It sees if it's in that set of instructions. So safe states any point where the instruction pointer is not in an atomic block or it is executing foreign code, and the collector will delay collection until it gets out of there. Okay, now code generator. I have a picture of the code generator. A Corman Lisp code generator is fairly fast and fairly dangerous. You can get into trouble with it if you go messing with it. It's so big. These 24-point fonts just look so big here, so huge. Anyway, another place that we looked at was the debugger, and of course, debuggers pretty much have to be thread aware. If you really want to get into debugging multiple threaded application, and all Corman Lisp really supports is the standard Lisp. The debug loop that most Lisps have that you fall into if you hit a break or an error or something. Well, what that does is it drops you into the executing thread, which may or may not be what you want. Usually probably is what you want, but it doesn't give you a direct way to get to other threads, to debug other threads. And what do you do if someone hits a control break or something, to drop into the debugger? Which thread do you want to debug? Well, it's something we have to still something we have to work on right now. You know, Corman list will drop into that thread, or we actually have a concept of the main list thread. It's sort of the main listener. You know, when you start up and you hit a control break, you'll drop into that one. But it's certainly an area that needs to be improved. Let's see. I don't think debugger behavior is not really mentioned in the standard. I don't think it's really an issue. I don't think it should be something that's standardized necessarily, but there's the Corman list debugger. That's actually, that's pretty much the way I implement it. Pretty much like that. You know, sorry, another non-standard feature that most lists seem to have, say, list image saving and loading. You could dump the whole heap. That's such a cool feature. I'm not really sure why it's not even a standard, but I'm sure it's not easy to implement in every system. But it is a very cool feature that I've seen in other languages. And, it was just an area that, I got hit a couple times in realizing, well, better not save the image if there's these other threads running. The system gets in kind of an odd state when threads are running. Yeah, Ken? Yeah, probably would. Yeah, I'll have to check into that. Thanks. A lot of this work I was doing about 5 years ago, and there wasn't even that much stuff on the internet then. It was so hard to get information like that. I didn't know where to look. That's all easily available now. It's great. Foreign threads. Well, these are pretty nasty, because if you want to be able to be called by any old thread that the operating system happens to create, then in our system, the garbage collector may not know about this thread. And in fact, it may not be set up properly with the right execution context, symbol table, and all of the things it needs to really live in this list world. So until recently, we didn't even support being called by any thread but the main, by any thread that wasn't allocated by Lisp. In the recent release of the Corman list, we added something called a direct call interface that lets other threads within an application call into Lisp directly, as if it was a callback, but it's not a Lisp thread that's calling it. And we added these little functions called blessed thread and unblessed thread, which the only rule is the application has to call blessed thread. The thread has to call it before it actually calls into Lisp, and that gives Lisp a chance to add it to its set of threads that it knows about. So the garbage collector will find it, initialize it, and everything. And that's done automatically if you create DLLs. The DLLs will automatically route set up the calls that they need to be made. I should let this. This is the ugliest one of the bunch, really. I'm sorry about this next one. But the foreign threads are really pretty ugly. Before it's been blessed, this is what it looks like. It's just like it'll wreak havoc in your system. Really. It'll take you all night to figure it out. So I am proposing a few changes. Well, basically, I'd like to see threads, some operations on multiple threads dealt with in the J13 standard. I've announced my intention to have Corman Technologies join the standards committee, and we're going to probably produce some kind of a suggestion. And I was just talking to Steve Havlitt, and he mentioned that there's it'd probably be difficult to get everybody to agree on what threads ought to do, but I think there has to be something, just because I think right now it's so confusing for implementers, and so I just suggest doing a doing a few additions, like specifying the dynamic variables have scope to a certain execution context, maybe introducing the concept of an execution context or something, and ultimately specify which objects, hash tables, packages, read tables, and things, which are safe for multiple thread operation and which aren't. Or maybe add, when you allocate a hash table, add a flag to say whether you want it to be safe for multiple thread allocation, which is something we did. Whether read, eval, and print, or I know those are just things I'm thinking of that, I hope, one of these days we can get into some kind of standard and get some agreement. So we can write multiple threaded applications that'll run on many platforms. And I like the Franz MP API. It's got a lot of good features. I don't like the without scheduling, without interrupts, but I think they're going away with the OS threads anyway. They seem like, from my reading of your documentation, we can add some nice classes, maybe, some mutex and critical section classes. And in summary, threads are good. They run in parallel by design, don't forget that. Lots of implementation issues. And basically illustrations, I think you'll all agree, illustrations really do help you to conceptualize things, get a better mental model. So, thanks. Is there a moment for questions? Anybody back there?
How does a compile function which sets a special variable know whether it's bound or not? If it's bound, you want to store the thread local version. If it's not currently unbound, you want to store the local version.
No, actually, it doesn't really make any. It doesn't have to know it's bound. There is a binding there, and whether it's compiled or not, that simple table entry is pointing to. Are you talking about at compile time or at runtime?
You have define food, which does the set queue start food.
Yeah.
And that's all it does. It doesn't bind it or anything.
Yeah.
Some other function may or may not bind it and you call food. Or if it bound it, it needs to be thread local. If it didn't bind it, it needs to be global.
Right. Well, once it's been bound, there's actually a check that's done in. If it hasn't been bound, there's a check done in the compiled code where it checks to see if there's a simple table entry for that symbol, and in that case, then it looks it up in the thread binding table. So in that case, it adds an instruction or two. But if it's been bound previously, I believe that's those instructions can be omitted. I don't know if that answers it completely. It's basically a check. There's checks at compile time, and there's also checks in some cases at runtime. But I mean, we didn't want to make the symbol table huge, and have to put all the symbols in there that you never mind. You don't combine that many. Yeah. Great.
Are these atomic sections of code, are those user definable as well?
Corman supports an assembler, and the assembler has, if you were writing an assembler, you could use those, and if you were writing, you could write these little code generator like macros that generate code with atomic sections, but there's not a way for a user to say, that this is an atomic state.
What I worry about is if someone coded an atomic piece of code, the garbage collector allowed the rest of the atomic code to run under the code. So then not only does the thread stop, but everything else stops.
Well, the code generator wouldn't generate an atomic block around a bit of user code that did something you didn't know about. It only does it on a very, maybe a few instructions. I mean, it's very, very atomic. Like maybe, it might be 3 or 5 or 6 instructions, and never around a branch, and never around a call. So, you're never going to see that. And I don't think there's anything a user could do that would, in their code would cause it to to happen unless they were using assembler. So it's all the list calls themselves are designed to be to be fine. And so this is not a substitute for like without interrupts. In fact, it doesn't keep other threads from running. It only keeps the garbage collection from running. So that's a difference. Yeah.
What would your estimate be as to the cost of supporting operating system level threads versus just supporting list level threads for the overall execution of programs, whether they use threads or not?
That's like a tough question. The cost of you mean the runtime cost, not the cost of implementing it. You mean the runtime. The runtime cost. Well, I mean, I'm assuming that overall one can get better performance with OS threads. I don't have any reason to think that you wouldn't.
I guess what I'm asking is, so you put in a lot of well, I don't know what to call it, a lot of mechanisms to support OS level threads. Let's say I was to write a program and I didn't even use OS level threads for any threading at all. How much penalty would I pay if you had just put in mechanisms versus if you had just put in mechanisms to support list level threads, or would there be any penalty? I mean,
Well, I don't think the threading really has significant overhead. But then I don't have the numbers to probably to substantiate that at this point. I think I'm done. Thank you. Yeah, I'm going to be here for the next 3 days. I'll be happy to talk to any of you about any of these issues. So.
Yeah, yes,